All right, so for the do now, couple questions. Number one is actually going back and reviewing salts. So looking at where does the salt come from? What acid and what base does the salt come from? And based on the strength of the acid and the base, that tells us information about the salt. And then number two, this is having us start to look at Ksp. We're going to focus on Ksp today and tomorrow. Doesn't take us very long. Today and tomorrow is Ksp. So for number one, label the following salts as acidic, basic, or neutral. So when we look at Na2CO3, remember that for the salt, we break it up into the acid and the base that it comes from. So the anions, so all of these anions, positive ions come from a base. Remember, an acid plus a base yields salt plus water. So Na will come from NaOH. Lithium will come from lithium hydroxide. Silver will come from silver hydroxide. And what we do with each of these is we think back to what type of base is this. So all of these are with hydroxide. Remember, we can look on the periodic table. Bring this one over here. We can look at the periodic table. Remember, lithium down, calcium down. It makes that lowercase b. Any of these cations with hydroxide is a strong base. So NaOH, is that a strong base? Yeah. So if NaOH is a strong base, that means that the ion that we're looking at, remember, you can only have one of two pairings. You can have strong neutral and weak weak. So if NaOH is a strong base, that means that Na plus is neutral. We'll just focus on the anions for all of these salts first. Lithium hydroxide, LiOH. You look at the periodic table. Is lithium part of that lowercase b? Yeah. So lithium hydroxide is also a strong base. That means that Li plus is neutral. And then AgOH, is silver part of that lowercase b? No. So silver hydroxide is a weak base. If we have a weak base, that means that Ag plus will be a weak acid. Because you have either strong neutral or weak weak. Then we look at the anions. So I'll put the anions in a different color. So here we have CO3 2 minus. So CO3 2 minus, we're thinking about the acid that it comes from, more than likely comes from H2CO3. The sulfide ion, S2 minus, will come from hydrosulfuric acid, H2S. And the chloride ion will come from hydrochloric acid, HCl. And now we have to think about the strong acids. We have the 7 strong acids that we need to know. Is H2CO3 one of the 7 strong acids? No. So this is a weak acid. H2CO3 is a weak acid. CO3 2 minus is a weak base. H2S is H2S. This is not H2SO4, this is just H2S. Is H2S one of the 7 strong acids? No. This is a weak acid, meaning that S2 minus is a weak base. And then HCl, is that one of the 7 strong acids? Yeah. So if HCl is a strong acid, that means that Cl minus is neutral. So now we have each part of the salt broken down. And now we just look at, is it acidic, is it basic, is it neutral? Thinking about it overall. Even though it's weak, it's still a base. So in terms of Na2CO3, we have neutral and a weak base. So we have neutral and basic. Well, that means then that Na2CO3 is basic. Li2S, neutral, and basic. Neutral doesn't matter, which means this salt is basic. So what is driving the pH in both of these would be CO3 2- and S2-. That's what's going to cause the pH to be above 7. And then we have AgCl. So we have acidic and neutral. Again, neutral is not going to do anything. So AgCl be considered an acidic salt. So when it comes to labeling salts as acidic, basic, or neutral, you just need to think about where do the ions originate from? Do they originate from a strong or weak base, strong or weak acid? And that's how we can figure that out. Then number 2, so this is kind of looking ahead to what we're going to focus on today. It says write the solubility product constant, that's Ksp. So write the Ksp expression for silver sulfate. So start by writing the formula for silver sulfate. So silver is Ag, carries a +1 charge. Silver always carries a +1 charge. Can never have any other charge. Sulfate, SO4 2-. So if you crisscross those to write the formula, silver sulfate is Ag2SO4. So solubility product constant is about an insoluble solid, or what we would usually consider insoluble. Unless it has potassium, nitrate, ammonium, or sodium, we always say it's insoluble. But every solid technically has a little bit of solubility. And Ksp is what lets us determine that. So silver sulfate, Ag2SO4 is a solid. Before we actually write the Ksp expression, so before we can write Ksp equals, we need to know what the equilibrium equation looks like. Every insoluble solid exists at equilibrium with its ions. It's going to look very similar to what we've looked at with acids and with bases and Kc and Kp. The ions that make up Ag2SO4 are 2 Ag plus ions. Remember, ions are always aqueous. And 1 SO4 2- ion. This is why writing the equilibrium equation is so important. People miss the coefficients. So if I want to write the Ksp expression, K is an equilibrium constant, like Ka and Kb and Kc and Kp and Keq. It's just another K, the last K that we look at. So an equilibrium constant expression, just like before, is products over reactants. Only include gases and aqueous solutions. So my products, I have Ag plus, but if I have a 2 out front, what's that going to look like in the expression?
To the power of 2.
Right, to the power of 2, it's going to be squared. Times SO4 2-. That's my Ksp expression. Why don't I have it over Ag2SO4? Why isn't Ag2SO4 in here? It's a solid. So this is our Ksp expression. It's just another equilibrium. Right? Just another equilibrium where we're looking at the ions. What's the molarity? What's the concentration of ions that we have in solution? Almost just like the common ion type of problems. Any questions on the do now? All right, so looking ahead at this week. So a couple things, I have the lesson plans up here. Took a screenshot of these after I think I updated them. So like the most recent version. We're going to focus on Ksp this week. And by this week, we're really focusing on Ksp today and tomorrow. Ksp does not take us long. It's not like titrations, it's not like buffers, right? You have an ice table and that's it. So we'll focus on KSP. So I said this just a little bit ago, I did move the lab back to Wednesday. So instead of everybody trying to rush to get it done tonight, it just gives people some time. If you haven't gotten your stuff in the class data table, do that today. And then you have some time to work on the lab. Calculations aren't going to take you long. I'm not pushing it back because the calculations are going to take a while. Pushing it back just because we were having some issues with opening the files in graphical analysis. So I had to like go into sheets and use the data and make a graph. So I just wanted to give everybody time to make sure that everything is in the data table because that gets recorded into your lab notebook, and then just give you some time, right? So you're not rushing on it. There's no rush on the lab itself. So that's going to be due Wednesday, and then you'll do it. You'll turn it in classroom like you have been. The rubric is in classroom, so if you want to see, it's also on the last page of the lab, so you can just see how it's graded, things like that. With KSP, it is very short, so the mastering that goes with it, I was debating on whether or not I even wanted to make a mastering, but I figured there's bonus that's built in. So the second part of mastering is 10 points. It's 9 questions. It's 9 questions, and 2 of them, I think, are the bonus questions. So it's not long. So it's actually like 2 of the questions are worth 2 points just because I wanted to make it 10 points. So it's not that they're harder. I just wanted to make it an even 10 points and have the bonus in there still. So that's actually due Thursday at 2:30. So like this Thursday, I'm trying to give some time to work on mastering, kind of built in. And so it's nice and short. After today, you can work through probably a good amount of it. And then after tomorrow, you'll be able to do all of it. And so KSP is the last part of Unit 8. So Unit 8 is kind of split into 2 parts. We have our acids and bases and our titrations and buffers, and then we have KSP. So I was trying to figure out when to put the test, but now that for the most part we're back, we don't have to do 2 test days anymore. So instead of doing Thursday, Friday, we're just going to do Friday for the test, which will give us Wednesday. I know we're short in class periods on Wednesday, but it'll give us Wednesday and Thursday to review. I'll give you guys the practice test and the study guide that I created tomorrow. I'll have those ready to pick up tomorrow. And so this test will be Friday. All right, multiple choice for your response like normal. And then you guys are actually off. We're all off on Monday, next Monday. So I just wanted to make sure that we got the test in before the 3-day weekend. I did not want to give you guys a test after a 3-day weekend. Figured you guys probably wouldn't want that either. Yeah.
What happens if I'm not here?
Well, then we just have to figure out a time for you to take it. Like, we'll figure it out. Whether you want to do it before or if you want to do it after, it's up to you. Yeah. So that's just kind of giving you a heads up for this week. I'm going to give you time to watch video 8.6 in class, not because it's long, but just to give you time. And then you'll actually watch 8.7 tonight. They're shorter videos, 10 minutes at most. And these are the last 2 videos in Unit 8. So then you'll see that there are no other videos the rest of the week in terms of stuff for Unit 8. So as you're looking and you're starting to review, remember that there's lots and lots of info on the class website. So now that we're under KSP, under Unit 8, there's also a page that's called Solubility Equilibrium. So if you want to look at stuff for KSP, there's lots of stuff for Unit 8. On Classroom, as you're starting to review for the test, there is some stuff on buffers that I posted on Classroom a while ago, just so you had extra practice. I'll put all that on the website as well. So that's just looking at this week. And then finally, some stuff for the lab. So on the data table, so I had some questions about finding the equivalence point. So, they said, I got questions that were like, based on our graph, what Where are we looking for our equivalence point? So on your titration curve, you have, let's say your curve looks like this. Remember that your equivalence point is about halfway up that spike in pH. And you're probably going to have to estimate, all right, estimate the best that you can. If you have 1 point here and you have one actual point here, you can average them to get the information. But you are looking for the pH and the volume of NaOH. So that you have both the volume of NaOH and the pH at the equivalence point. Obviously, the strong titration, the pH should be 7. But your strong, weak titration is not. So then, remember, this goes into your lab notebook. Make sure you go to your class periods tab. So you guys are the first tab. So not an issue for you guys. But this is what gets copied in. Just make it look like the data table in your lab handout. You do not need the group initials in your lab notebook. If you put it in, that's fine, but you don't need it. You guys will not have 8 trials like the other classes, I don't think. So just put however many trials are in the class data table. Remember, for the calculations, you want to use the averages. So the point of the bottom row of the data table, it says average, is to average all of the values. Because the more trials you have, right, the more precise your data can be. So you're going to take averages of each of those, and you want to use the averages for the calculations. And the calculations are, what's the molarity of each? What's the moles? All right, so things that we've looked at before. You might want to add this somewhere, whether on your lab handout or somewhere that you can refer to it, because one of the post-lab questions has you compare your molarity that you calculated to the actual molarity. So if on like the post-lab question page, the HCl concentration was 0.0984 molar. We tried to get it as close to 0.1 as we could, but as we were diluting, it wasn't quite. So HCl was 0.0984 molar. Acetic acid was 0.1 molar. So when you're calculating, if you get, 0.11 molar, you were close. But one of them says what may have caused it to be different. So that's your source of error type question. So just make sure you have those written down as well. Any questions on the lab? If you find that you're trying to open the data and it's not opening, if you email it to me, I know I have one email that I need to do it for. I got it this morning. If you can't open it, if you actually send the file to me, email it to me, I can open it as a text file, put it in Google Sheets. I think it's what I had to do. It's what I had to do for third period, and then I sent it to some people who didn't have the graph first period. So I can actually open it as a text file, put it into Sheets, and I can share it with you and make you the owners that it's your file. So if you can't open it, don't think like you did something wrong. Just email it to me. I can go through and I can get everything back for you. All right, so now we're going to go back to Ksp. So we're now moving away from acids and bases in terms of some stuff in Unit 8, and we're focusing on solids. So this is the second half. So we have like the first half notes, the second half notes. So if you need the second half notes, I do have some extra copies over on the side. But with the second half, we're focusing on these insoluble solids. With molar solubility and with Ksp, slightly soluble salts involve an equilibrium between a solid and its ions. So we've been calling solids insoluble. Technically, every solid has some degree of solubility. Technically, solids can dissolve even a little bit. So that's what Ksp focuses on. We talk about a saturated solution. A saturated solution means that you've dissolved just enough solid into solution. It could be a tiny, tiny amount. But if some has dissolved, then you have to think about equilibrium. So then we have a couple terms that we focus on. One of them is molar solubility. So molar solubility is the number of moles of solute that dissolves to form a solution. It looks similar in terms of units. It's moles per liter. We know moles per liter as being molar. Technically, solids don't have true concentrations with equilibrium, which is why we don't include them. But based on the number of ions that exist in solution, we can figure out how much solid dissolved. So the goal of using molar solubility and using Ksp is to figure out how much of what we consider an insoluble solid actually dissolves in solution. And molar solubility is that. It's how much solid dissolves. Solubility product constant. Solubility product, Sp. That's where we get Ksp. So Ksp is the equilibrium constant for equilibrium between a solid and its ions. So we focus on the ions. We focus on the concentration of ions in solution, and then based on how many ions we have, it tells us how much solid dissolved. And we're going to look at finding Ksp, and we're going to look at finding molar solubility. So some of the questions that I saw from the video were, what are the different types of questions that we will see with Ksp? How is this different from what we've been doing? It is not different than what we've been doing. It's the same process. We have an ice table, we have something initially, we're finding something at equilibrium, we're using an equilibrium constant. We're just applying it to a different situation. So this is going to be more like the Kc that we looked at before, acids and bases. We will look at some common ion today. We'll look at much more common ion tomorrow. So if we look at example 1 is at the end. Let's see. Much shorter notes packet. Example 1 is on page 4. So today we're going to focus on examples 1 through 5. Example 1. So there are a few different parts to example 1. The first one says if the molar solubility. So here are some terms that we're looking at. Molar solubility of calcium fluoride is 1.24 times 10 to the negative third moles per liter. What is Ksp at this temperature? So before we do any math, before we try to plug things in, there are always two things that I want you to make sure that you have. The equilibrium equation, so the balanced equation, and write the Ksp expression. So we have calcium fluoride. Because it's talking about molar solubility and it's talking about Ksp, that tells us that calcium fluoride is only slightly soluble. It's a solid. It's talking about molar solubility of something. That means that that something is a solid. And if we're solving for Ksp, that means it exists at equilibrium. Notice how this does not involve potassium, nitrate, ammonium, or sodium, because only potassium, nitrate, ammonium, and sodium are 100% soluble. So like strong acids don't have a Ka, or the Ka is very, very large. Same thing for solids that include those 4 ions. Potassium, nitrate, ammonium, sodium are 100% soluble. They don't exist at equilibrium. Since this does not have one of those ions, we're going to write the equilibrium equation. So CaF2 has 1 Ca2 plus ion and 2 F minus ions. This is why writing the equation is so important. Don't forget the coefficients. And because it's asking for Ksp, I'm going to go ahead and just write the Ksp expression. K is an equilibrium expression. No matter what the little subscript is, it's always products over reactants, and you do not include solids and liquids. So for this, I'm going to have the concentration of Ca2 plus times the concentration of F minus squared. because the coefficient in a balanced equation becomes the exponent in an equilibrium expression. So now I have those two things. And this is going to be useful because I can't tell you how many people will miss that too, that squared. So this is telling us the molar solubility. I know in the example in the video I used X's, but I saw another teacher do it and she used S for solubility. And it kind of helps thinking about solubility. So I'm going to use an S here. You want to keep using X's, you can keep using X's. It's the exact same thing, it's just a variable. So this is the solubility. This represents S. Because we have K, we have equilibrium, we're going to focus on an ice table. Now this ice table is going to be a little bit different. So initially, we have some solid. How much do we have? Oh no, it doesn't matter. Doesn't matter how much solid we have. But we don't have any ions. If the molar solubility, that is how much dissolves. That is how much dissolves. So this, in my change, 1.24 times 10 to the negative third. See how it's moles per liter? Remember in an ice table we need molarity. It's moles per liter. So we have 1.24 times 10 to the negative third dissolve. And at equilibrium for the solid, we have some. Right? Doesn't matter how much we have. What matters is how much solid dissolves. So now, calcium fluoride to Ca2 plus is 1 to 1. So if 1.24 times 10 to the negative third dissolved, that's how much Ca2 plus we have. What's going to be different about F minus? 2 times as much. You have to take into account the ratios. 1.24 times 10 to the negative third calcium fluoride dissolved. We expect 2 times that of the fluoride because of the ratio. So at equilibrium, we have 1.24 times 10 to the negative third moles per liter of Ca2 plus and 2.48 times 10 to the negative third moles per liter of F minus. I always get the question like, why aren't you worried about the solid? Well, I'm not worried about the solid because it's not in my expression. It doesn't matter how much solid we have. I could have 1,000 grams of calcium fluoride. But the important thing is how much of that dissolves, because it doesn't matter. If I have way more than can dissolve, it's just going to sit in the bottom of a beaker. So this is what is important. Molar solubility is what goes into the ice table. And then we just plug into Ksp. Now, just kind of looking right now, before I even plug it in, what do you think is the most missed thing when we plug in from an ice table to Ksp? Looking at, like, as I write this out, 1.24 times 10 to the negative third times 2.48 times 10 to the negative third. What did I not do here? Square it. Pay attention to the Ksp expression that you wrote. All right, pay attention to the expression that you wrote. That's always why I say write the expression first. So 1.24 e negative 3 times the quantity, 2.48 e negative 3 squared. Ksp, 7.63 times 10 to the negative 9. And just like Ka, Kb, Kc, Keq, Kp, right? Ks don't have units. A small value of Ksp, right? I would consider 10 to the negative 9th pretty small. That means that not much of this dissolves. Because remember, Ksp is about the number of ions. If there aren't very many ions, if this is a small number, that means that not very much of the solid dissolved. So if we look at part B, it is found that 1.1 times 10 to the negative 2nd grams of strontium fluoride dissolves per 100 milliliters of aqueous solution at 25 degrees Celsius. Calculate the solubility product of strontium fluoride. So solubility product, that's Ksp. It wants us to calculate Ksp. So again, you always want two things. You want the equation. Here's the equation. I'm going to add states of matter, though. Here's solid, aqueous, aqueous. And then I'm going to write the Ksp expression. So Ksp products over reactants, but I don't include the reactant because it's a solid. Now, in order to plug into the ice table, remember we either need atmospheres or molarity, moles per liter. I'm not dealing with gases, so I'm not going to worry about atmospheres, which means we need moles per liter for this ice table. So need moles per liter for the ice table. They give me grams per milliliter. I'm going to just do it up here so that everybody can see it. So 1.1 times 10 to the negative 2nd grams. And they give me per milliliter. I can convert milliliters to liters pretty easily. That's 0.1 liters. So right now I have grams per liter. In order to plug it into an ice table, we need molar solubility. We need moles per liter. So at this point, I need to go from grams of strontium fluoride to moles of strontium fluoride. You can go from grams to moles by using the molar mass. I'll just give you the molar mass because I calculated it this morning. 125.62. This is strontium fluoride. So what I'm doing right now is I'm converting the solubility in grams per, technically milliliters, but grams per liter to moles per liter. That's what we need to go into the ice table. I'm going to keep it to 3 sig figs for now. 8.76 times 10 to the negative 4th moles per liter. Now, instead of moles per liter, could you just say molar? Yes, it means the same thing. So if I focus on this ice table, initially for the solid, I have some amount of solid. We don't care how much we start with. It doesn't matter how much we start with. But I had 0 ions. Then it says it is found that now this much strontium fluoride dissolves. So that means that we had 8.76 times 10 to the negative 4th moles per liter dissolve. Which means at equilibrium, we're still going to have some amount of solid. Who knows how much? What we care about is how much dissolves, because that will help us figure out both of these ions. So if 8.76 times 10 to the negative 4th moles per liter of solid dissolves, because strontium is 1-to-1 with strontium fluoride. We're going to expect to see that much Sr2+. What about F-? We're going to have the same amount? Make sure you take into account those coefficients. So we're going to see 2 times 8.76 times 10 to the negative 4th. So then at equilibrium, we have strontium and we have fluoride ions. These equilibrium numbers, these equilibrium values are what go into the Ksp expression. Right? Ksp is how much of the solid dissolves. Well, it's based on the ions that exist in solution at equilibrium. So 8.76, 10 to the negative 4th. All right, pay attention to the Ksp expression you wrote. You have to take into account the 2 in the ice table, and you also have to take into account the Ksp expression. So times 8.76, E negative 4. Ksp. I don't want to do 2 sig figs. 2.7 times 10 to the negative 9. If you did 3 sig figs, it'd be 2.69 times 10 to the negative 9. Again, relatively low Ksp, but that's what we expect for what we consider an insoluble solid. Not very many ions in solution. Questions on A or B? So then for part C, so now this has us going backwards because now they give us Ksp. So they give us Ksp, and now they're saying, what is the molar solubility? So the Ksp of barium iodate is 6 times 10 to the negative 10. Now, what if they didn't give us Ksp? Well, again, on a test or a quiz, you're going to be given Ksp. What if you're working on mastering and you need Ksp? Remember I said when we had Appendix D, we had the Kas on the front and the Kbs at the top of the back. Well, the back, most of the back page of Appendix D are Ksp values. So if you need a Ksp value for mastering, you can use Appendix D. And it will probably tell you use Appendix D to help you. So just keep that in mind. I've tried to give the Ksp values in the notes though. So the Ksp for barium iodate is 6 times 10 to the negative 10. What is the molar solubility of barium iodate? So they already gave us equilibrium reaction. Let's write the Ksp before we do anything else because I see that there's an equilibrium arrow here. So if I add states of matter, we have a solid and then our ions are aqueous. That's always the case if we have an insoluble solid or a slightly soluble solid. So I'm going to have the concentration of Ba2 plus is the concentration of IO3 minus squared. So now we're going to focus on the ice table. Now this is going to be a little bit different. Right? Now they give us Ksp. And we're solving for solubility. So this is where I like to use the S. Because then when we solve, we know that S represents solubility. You can use X, that's fine. It's really up to you. So for all of this, and we have some solid, we have S amount dissolving. And we have some solid after. Solid, we are not concerned about. What we're concerned about is what happens in terms of the ions. So initially, it says nothing else about any ions. So those are 0. Barium iodate. S is the solubility. We have S amount that dissolves. Barium is a 1-to-1 with barium iodate. The iodate ion is 2 times that. So at equilibrium, we have S amount of barium 2 plus, 2S amount of iodate. Again, if you want to use X's, X is going to be the same thing. This is now what gets plugged into Ksp. It looks very similar to what we've done before. The Ksp value was given to us. 6.0 times 10 to the negative 10. Ba2 plus is S. Iodate, IO3 minus, is 2S, and we need to square that. The algebra might be the most difficult part of Ksp. Not the numbers, not plugging in, but the algebra. Because if we look at this, 6 times 10 to the negative 10, we have the quantity 2S squared. That means you need to square the 2 and you need to square the S. 2 squared is 4. So when we look at this, S times 4S squared. So 6 times 10 to the negative 10 is 4S cubed. Be careful with the algebra. And then we solve. Now, there were some questions about what would this look like if this were multiple choice? Would I have to do the cubed root in my head? No. Right. Maybe the square root, but not a cubed root. So I'm going to start by dividing by 4. So 1.5 times 10 to the negative 10, I think. Six e negative 10 divided by 4. Yes. That equals S cubed. So I think if you have a graphing calculator, you can hit math 4 is cubed root. Right, math 4 is cubed root. Or you could take it to the 1/3 power. That's also cubed root. All right, so we would take it to the cubed root. Cubed root of 1.5 times 10 to the negative 10 is 5.31 times 10 to the negative 4th. Right, and this is labeled S, which tells me this is my solubility. This is how many moles per liter of solid dissolves. So if you're solving for solubility, the biggest thing is making sure that you can take the cubed root. Maybe the 4th root, but we usually just see the cubed root and the square root. So we usually see the cubed root and the square root. Questions on number 1? Yeah.
If they asked the solubility of 2 IO3, would we just multiply it by 2?
Yes.
Okay.
Yeah, if they were to say what concentration of IO3 minus do you have, then here's S, you multiply by 2, that'd be your IO3 minus. Yeah. When it asks for molar solubility, that's talking about the solid. So in this case, it says molar solubility of this. We know that's S. And then, yeah, we could figure out that's the same as Ba2 plus. We multiply by 2, that's IO3 minus. So I want to have you guys see if you can at least set up part A. So for example 2, we have PBI2. So start by writing the equilibrium. All right, write the equilibrium equation and write the Ksp expression. Then part A says calculate the molar solubility. So that's just like what we did in part C. Calculate the molar solubility. And then if you want to see if you can go from molar solubility, which is moles per liter, part B wants you to go to grams per liter. So see if you can work through example 2. So as you're finishing up, I answered A and B up on the board. So you can see how I went through, calculated S for the solubility of PDI2. Solubility out of Ksp is moles per liter because you need moles per liter or molar to go into the ice table. So this is molar or moles per liter. Part B wanted us to take 1.21 times 10 to the negative third moles per liter and go to grams per liter. So I said 1.21 times 10 to the negative third moles per 1 liter. Use the molar mass to cancel out moles and get grams over liters. All right, so for example 2, we have all the work up here. Molar solubility means you're looking at moles per liter. And then if it says calculate the solubility and it tells you in grams per liter, then you're just going to make sure to convert your moles to grams. It's otherwise the same thing. So example 3, there was a question on what would a multiple choice question look like. So I had this in our notes as our example number 3, just so we can see, like here would be a Ksp question that doesn't involve a calculator, and you'll actually see that it doesn't really require any math besides, you know, squaring or cubing something. So example 3, again, notice it says no calculator. We're going to try to get used to not using calculators for multiple choice questions. So a saturated solution of cadmium 2 phosphate can be represented by the chemical equation shown, which expression relates the solubility S to the Ksp. So notice we're solving for S when we have Ksp. So here's our balanced equation. Let's write the Ksp expression. So before we do anything else, let's write the Ksp expression. Products over reactants. This is a solid, I'm going to ignore it. So I'm going to have the concentration of Mg2 plus cubed times the concentration of phosphate squared. Now we're relating solubility. Now whether you use S or X, it doesn't matter, but just remember that if you use X, that is S. So if we think about an ice table, right, remember solid doesn't really matter except that we are using up S amount. Right? S amount, the solubility is what is dissolving. Doesn't say anything else about us having any other ions in the container. So what would my change be for the magnesium ion? If you look at the coefficient, it's going to be 3 times the solubility. And phosphate is going to be 2 times the solubility. So at equilibrium, we have 3S and 2S. And so we're actually going to just plug that in to Ksp. So Ksp, so for Mg2 plus, it's 3S. This is why writing the expression is so useful. Bring this cubed root or cube down. Phosphate, 2S. Bring the squared down. Now, right, here's where we have to think. Because if we're practicing doing it without a calculator, 3 cubed. Not 3 times 3, but 3 cubed. I will not lie to you. This is how I do it. Off to the side, I'm like, okay, 3 squared is 9. 9 times 3 is 27. So 27 times S cubed. That's 3S cubed. And then 2S squared. So times 2 squared is 4, S squared. Oh, 27 times 4. 27 times 4 is 8 to 108. Right? 108, yeah. Sometimes you have to do the math off to the side. I can't do 27 times 4 in my head. If you can, awesome. Or I just choose not to. So I just multiply off to the side. Some people will do 27 times 2 and then add those together. So 54 plus 54. Either way, though, we have Ksp. Whoa, that is supposed to be a little s. That's fine. So 108 times add them together. S. So then the whole point of this is to solve for Ksp. All right, so for these S's, you add those together. You're just multiplying, or you're combining the like terms, you add those together. So if I'm solving for S, the first thing I would do is divide by 108. That equals S to the 5th. And then to get S, I would have to take the 5th root. Take the 5th root of each side. Here's what gets us S. So look and see which one of those matches, and that's D. Notice how A looks similar. A is what you would get if you multiplied these instead of added them. The only time you multiply is when you have, so if you had like S cubed squared, that's when you multiply. If you have S cubed times S squared, you add them together. So for example, 3, our answer is D. So it did involve some math, but we didn't have to actually do like a cubed root, or we didn't have to do a 5th root, but it required us to do 27 times 4. So the next one that we're going to look at is kind of looking ahead a little bit, kind of looking ahead to tonight's video. But we'll work through this because I think that we've seen enough of these questions that we can go through. So for example 4, it says calculate the molar solubility of AgBr. They give the Ksp in 3 different solutions. So A is pure water. That's just what we've been doing. We've been doing it in water. Then in a silver nitrate solution, and then in a sodium bromide solution. So let's start with the pure water, just like we've been doing. AgBr. So I'll start with writing equilibrium. And I'm just going to write the Ksp expression up here, so I just have it one time. So Ksp is Ag plus times Br minus, a nice 1-to-1 ratio. So in pure water, right, here's where our initial and our equilibrium don't matter for our solid. Pure water means I don't have anything else, so these are 0 initially. So I have plus S for the solubility of Ag plus S for the solubility of Br minus. So this one's a nice Ksp, 5.0 times 10 to the negative 13. Ag plus is S, Br minus is S squared. So for this is S squared. So to solve for S, Take the square root. 7.07 times 10 to the negative 7. Remember, solubility is moles per liter or molar. Just like what we've been doing. Now, let's look in part B. So I'm going to write my equilibrium again. I have a solid silver bromide, and it's at equilibrium with its ions, Ag plus Br minus. Again, the only thing that we care about in the solid is this change. That's our solubility. We don't care about initial or equilibrium because it's not in the expression. Now, here's where it gets a little bit different. It's nothing you haven't seen before. Because now we are in an AgNO3 solution. So now in the beaker, not only do we have the Ag plus and the Br minus from the solid, now we also have Ag plus and NO3 minus from the solution. The only thing that this does is it gives us an initial amount of Ag plus. This is a common ion problem. So AgNO3, this is our concentration. AgNO3, it's 1-to-1 for Ag. Br minus is still 0. Now, we have 3 times 10 to the negative second plus S and S. Well, I guess that should be what it is. This would still be plus S. Wrote my equilibrium too soon. Here we go. It's a common ion. So we've seen this common ion before. So Ksp, 5 times 10 to the negative 13. What is that? 1, 2, 0.03. I'm just going to do it in standard notation. Three times 10 to the negative second is 0.03. I'm just doing it to avoid scientific notation. Now, if you look at this at first, you're like, oh, that's going to give me quadratic. What did we do before to prevent quadratic? Assume x is small, or s, right, in this case. Assume our value is small. We assume our value of s is so small it's not going to impact that 0.03. Now we solve. So 5 times 10 to the negative 13 divided by 0.03. My solubility is 1.67 times 10 to the negative 11. So if it's not in pure water, we're going to have some sort of common ion. If it's in pure water, we have 0 ions initially. See if you can do part C. See if you can do part C. Use part B as an example. But now it's an NaBr solution, so look for where the common ion would be. Right? What would be the common ion there?
Well, you don't have to add it to the 3 times 3.
So for this, you mean this plus S?
No, like your final answer.
Oh, no, because when you're solving for molar solubility of AgBr, so you're actually solving for this amount. You're solving for S. If it asked how much Ag plus would you have, then you would add it to the 0.03.
Okay.
So now because we're in a 0.5 molar NaBr solution, NaBr is a strong electrolyte, breaks apart completely. So that means that initially we have 0 Ag plus, but we have 0.5 molar Br minus. So we can actually do 5e negative 13 divided by 0.5. Remember that S stands for solubility. So your unit is either moles per liter or molar. So if you notice here, right, pure water was just the solid at equilibrium. As we add a common ion, solubility was times 10 to the negative 7 on its own. As we add a common ion, right, negative 11, negative 12, solubility decreases as you add a common ion. This is actually what video 8.6 is on. What affects solubility? Common ion is one of them. Questions on example 4 before we do the last one. Okay, so example 5. Which of the following salts is most soluble? Right, most soluble at 25 degrees Celsius. Now, this was something from College Board down here at the bottom. You cannot always compare Ksp values when you're looking at what is most or least soluble. Yes, the smaller the Ksp, the less solid dissolves. But if you are looking at different salts, unless they are the same ratio, so like AgCl and BaCO3 are 1-to-1 ratios. If they are 1-to-1 ratios, right, or if they're all 1-to-2 ratios, then you could compare Ksp. But if they are not all the same ratio, you cannot compare Ksp. You want to compare the solubility, because the solubility has taken into account all of the ratios. So in this example, I set this table up for you. So we have the salts, we have the Ksp value. Then I have you write the Ksp expression. Now to write the Ksp expression, it would probably be useful to have the equation. You can see it, right? You can kind of see it in your head. Just write the expression. But then I actually want you to solve for the solubility. So it's kind of 4 questions in 1. So I'll do the first one, and then I'll have you guys do the next 3. I'm going to write my equations down here at the bottom, just so that I can see it. So I'm going to start with magnesium hydroxide, right, MgOH2. Well, that's at equilibrium with Mg2 plus and 2OH minus. So my Ksp expression is Mg2 plus times OH minus squared, because magnesium hydroxide is a solid. So if I want to solve for the solubility, once you start doing these questions, a lot of times people can simplify the ice table. If you simplify the ice table, that's up to you. Here's what I mean by simplify the ice table. Because this is all in pure water, I'll just see people do S and 2S, which is fine. Because you're showing the equilibrium row, you're showing the important row. And then, right, when we solve for solubility, I'll just show it up here. What's the Ksp? 1.8 times 10 to the negative 11 equals, here's my expression, here are my values. S times 2S squared. Just be careful with that algebra, because that equals, this is 4S squared, That equals 4s cubed. So to solve for this, I do 1.8 e negative 11 divided by 4. And then take the cubed root of that. Again, cubed root is math 4 on the graphing calculator. 1.65 times 10 to the negative 4th moles per liter. So there's the solubility of the first one. I want you to go through and see if you could do the next 3. Lanthanum iodate might take a little thinking. Now you get a calculator on this whole thing, but just be careful with that one. That's why I'm having you write the Ksp expression first. I'll go through as well, filling the table. This also gives us some practice with thinking about the charges of all of these ions. And once you have them all solved, once you've solved for all the solubilities, you can put them in order. All right, you want most soluble. Most soluble means you have the most number of ions. So which one has the most number of ions? The most soluble is the highest solubility value. All right, so here are all the solubility values that I got. So for this one, all right, for lanthanum iodate, so I didn't write all of the equations out, but underneath I just put S and then 3S, because there were 3 times as many iodates. And so when I plugged it in, it was S times the quantity 3S squared, which is S times 27S. So I divided by 27, but that left me with S to the 4th. So in my calculator, I actually just did what the number was, 2.77778 times 10 to the negative 13. In my calculator, I actually just did that number in parentheses to the 1/4 power to take the 4th root. And so when you get the solubility, you get 7.26 times 10 to the negative 4th. So in terms of solubility, the most soluble is the one with the highest value of S. So I noticed that magnesium hydroxide is times 10 to the negative 4th, but so is lanthanum iodate. So then look at the number in front of the multiplication. 7.26 is greater than 1.65. So the most soluble is lanthanum iodate. And we could put them in order, right? Next would be magnesium hydroxide, then barium carbonate, then silver chloride. But if I did it based on the Ksp values, all right, based on the Ksp values, if I just compared those, I would say, oh, barium carbonate, that's the most soluble. But that's not actually the most soluble because all of these are different ratios. So it's best to compare the solubilities, the value of S. Any questions on this last example? Yeah. Yes. And I'll put this up here. So that was the last example we were going to do. The next thing is I'm going to give you time to actually watch 8.6. There you go. So I'm going to give you guys time to watch 8.6. It's, I want to say 10 minutes. And then you'll watch 8.7 for tomorrow. So I wanted to give you time in class just so that I didn't have you watching 2 tonight. If you'd rather just wait and you're like, I'll just watch them both tonight, then okay. But 8.6 and 8.7 will kind of go one into another. And then 8.7 is the last video in the unit. Just again, the lab is due Wednesday, so no need to rush through the lab trying to get that done tonight. You'll have the time now. You'll put in headphones. All right, watch 8.6. If you want to go right into start watching 8.7, that's fine. I want to say one's 10 minutes and one's 8 minutes. So